Every day for 7 years.
Continuously, or you just go through the motor?
I don't know about that. I haven't had any experience with that.
7 years.
It sounds like
Okay, you guys ready?
Yeah.
Ready? Good. Okay. What's the meeting in the corner? Jeff, I just listened to a show on radio the other night about organized crime, and you're just reminding me of a Godfather there, sitting there with your black turtleneck and your whole entourage around you, and Chris is your hitman. You're saying, shut up. All right. It was a David Brudnoy thing. Ever listen to David Brudnoy? He's got this ridiculous collection of people that he interviews, and somebody calls up, and the person who calls up claims that he is in fact a hitman. The most peculiar conversation I ever heard. So David Brudnoy can't figure out if the guy's just pulling his leg and making him look stupid or if the guy's serious. But the guy was really peculiar, so it almost seemed like maybe he was telling the truth. And David Brudnoy finally resorts to, well, can you tell me who you work for, like what the family name is? And the guy goes, no, I can't tell you that. So finally goes, well, if we can't really get any more details here, I'm not really sure this conversation is going to get so interesting, so thanks for calling. Something like that. It's like, tell me some blood and guts. Tell me who you killed last, right? So he goes, why do you do it? I forget what why do you do it or something? And the guy goes, oh no, the guy calls up, he goes, we just got to stop the killing. We just got to stop the killing. So he goes, okay. My producer tells me you're a hitman. What do you mean we just have to stop the killing? You know, we just have to stop the killing. All right, well, why don't you just stop since it's your job? So the guy goes, then he says, well, if we stop the killing, correct me if I'm wrong, but isn't your job like a hitman? You make your living out of this. So if we stop the killing, you're going to have to go on welfare or something. You'll need to make some money. And the guy goes, oh, no, I'm a multi-millionaire. Anyway, it's out of control. It was my ride home last night. Let's talk about dynamic programming.
All right.
Dynamic programming. All right, yeah. if we have to. Here's a teeny review of what we did yesterday because I want to remind you of a very, very important point that I mentioned. And that is that sometimes it's better to make a problem seem harder and actually the problem becomes easier. And the example that's really nice is the example where we had the single source shortest path. We had 3 different methods to do it. None of them were recursive methods. They were all these iterative methods or all these methods that relaxed the vertex and then went on to scan the next one. They were completely iterative. In fact, I never even sat here and said, let's come up with a recursive way, because there isn't any good one for single shortest paths that's natural. But if you make the problem harder, suddenly it encompasses enough ground to have a recursive structure. And this happens also in mathematics when you're doing proofs by induction. Sometimes you're trying to prove something that's too constrained, and your inductive assumption doesn't give you enough to make the next step. So you actually add more to your proof, just so that your inductive assumption's bigger, and then you can actually leverage enough to get to the next step. It's really the same idea, but here it's more concrete because it's an algorithm. So how would you normally come up with a recursive structure for shortest path? That's what we did yesterday, more or less. Here's what it looks like. I got a graph. I got node number 1. I have node number 10. I want to find the shortest path from node number 1 to node number 10. How do I do it recursively? Well, why don't I find out the shortest path from 1 to 2 and then 2 to 10? And I'll figure out the shortest path from 1 to 3 and 3 to 10. And I'll figure out the shortest path from 1 to 4 and 4 to 10. And I'll add these two together, I'll add these two together, I'll add these two together, etc., all the way through all the possibilities. And I'll take the one of these that's the minimum. Right? That's a recursive problem. Find the shortest path from here to here and here to here, add them together, take the minimum of all of these. That's more or less what we did yesterday. Except the thing is, this isn't recursive if it's a single shortest path. Single shortest path says, I want the shortest path from here to 10. That has to be in terms of from here to something else. But this is in terms of other nodes to other nodes, not just one to other nodes. So that's what gives you the clue. Let's make the problem harder and try to find all the shortest paths from every node to every node, because now my recursion is okay. Right? So that's a good principle in general in algorithms. You can bump up your problem harder and get a recursive structure. And that's what we did yesterday. So we did something just like this. Except in each step, we added an extra edge to the situation. So we had all this computation for when there's one edge in the path, and then all this computation for when there's two edges in the path, and all this computation for when there's three edges in the path. And each one of these computations took n for each pair of vertices. So that was n squared times n is n cubed. And we did it n times to make sure we got enough edges in all the paths. So that made n to the fourth. And we thought about it, and we realized we don't really have to do it n times. We can do it log n times if we say that we have the shortest paths that have one edge in them, and then the shortest paths that have two edges in them, and the shortest paths that have four edges in them, and then we can double up and take advantage of the log. So the best we could do when we were all done was n cubed log n. It's not too bad. It beats some of the repetitive n versions on the regular shortest path algorithms, but it doesn't beat all of them. And we'd like to do better. We'd like to get it down to n cubed. And the way we're going to do better is to do a similar idea, the same kind of thing. The shortest path from here to here is the shortest path from here to a middle spot, from the middle spot to the end, over all the possible middle spots. But we're going to be a little more careful with how we move from number of edges in a path. So instead of saying there's going to be one edge in the path, or two edges in the path, or three edges in the path, that's what made us go through all these middle spots. We're going to try to fix it up and increase the cases so that we don't have to consider all the middle spots. And that's what Floyd-Warshall is doing. It's just a better recursive structure that ends up not having to do n to the fourth, ends up only doing n cubed. And it's not too tricky once I show it to you, and it'll be even actually easier to write down and implement than the one we did yesterday. The hard part is thinking of the recursive structure. Okay, questions about it? All right. When I show you this recursive structure for the Floyd-Warshall all-pair shortest path, you're going to notice that it's similar to an idea that we did the other day in binomial coefficients, and it's similar to a lot of other ideas that you'll see in other dynamic programming problems. Basically, the idea of if you want to figure out the value of a particular case, you want to divide it into two choices. One where you include a particular one of the many values, and one where you don't include that one. Remember when we did n choose m, and we did it in terms of n minus 1 choose m minus 1, and n minus 1 choose m? We either included that special mth value or we didn't, and we got two cases out of it. That's what we're going to try to do here, and getting two cases out of it is better than having to do n cases. And that's where the improvement is going to lie. So I'll show you more specifically right now. Okay, other questions before we go on? All right, so let's write down a relationship. The shortest path from x to y. And the key thing is what this k means. Before, dxyk meant the shortest path from x to y where we have at most k edges in the path. That was a natural way to do it. Then we built it up as k went from 1 all the way up to n. And each time we built it up one more time, we had to consider all the possible middle spots of smaller paths. Now we're going to make this mean something different. It's still the shortest path from x to y. But this k does not mean that it has k edges at most in the path. Instead, it means the shortest path from x to y that uses nodes 1 through k. In the middle. So order the nodes to your graph. They're ordered 1 through n. And we're going to go through them one by one. And as we go through them and add new nodes into our list, as k gets bigger and bigger, we're considering the shortest paths between 2 points where we're allowed to use the vertices from 1 up to where we're up to. Let's write an example of a graph on the board and just make sure that this makes sense. Okay, here's a graph with 5 nodes. Let's calculate the following. dxy 0. dxy 0 means that you are allowed no intermediate nodes at all. None. No nodes can appear in between the x and a y in a path. So what is dxy 0?
Direct distance.
It's exactly what you see here on the board. The shortest distance from D to A is 2, with no nodes in between. It's paths that have exactly one edge in them. It's exactly the equivalent of what we started with last time. But this is the only time that it's exactly equivalent to what we did last time. After this, the subsequent D values are going to be different from what we did last time. So dxy 0 is all the shortest paths that don't have intermediate nodes on the path, that are either a direct edge or else infinity. So it's just what you see there. It's exactly the input of the data structure. And since this is a 2-dimensional array, it's exactly the input of what you get when you start the problem. OK, let's do this. dxy 1. We're going to imagine this is in alphabetical order. So 1 means the vertex A. We have added A into the picture. A can now be an intermediate vertex. So let's do some particular examples. What's the shortest path from D to B? If A can be an intermediate vertex, it's 3. What's the shortest path from B to C if the only intermediate vertex allowed is A? It's 2. It's only that direct edge, right? Let's see. Nothing else is very interesting, yeah. I picked one rotten example. Right now, what's the shortest path A to C? When you're allowed to use A as an intermediate node. From A to C. You can't get from A to C when the only intermediate node allowed is A. So the answer is, as far as we know now, it's infinity. What if I said, go from A to C, but now you're allowed 2 nodes, namely A or B as intermediate vertices? Then what's the shortest path from A to C? Then it's 3. Okay? This number here represents the collection of nodes from 1 up to that number that are allowed to be intermediate nodes. They don't have to be. You can use any subset of them. But the best you can do using those and only those as intermediate nodes, no other ones. Okay? So it's a different formulation than what we had before, a different recursive structure, and maybe not as natural as what we had before, but faster to actually calculate. All right, questions about this? Michael? No. Okay. Think about that combinatorial problem, and let's try to figure out a recursive relationship for dxyk. You want the shortest path from x to y that uses nodes intermediate that are numbered 1 through k. So there are 2 choices. Okay, I'm going to divide all the possibilities into 2 choices. One is that the node k is helpful, that you actually get a shorter path because you've added the node k in, or adding in the node k doesn't do a darn thing. You still get a shorter path from some other way. That intermediate extra node that you have a choice for doesn't help. One of those is going to give you the shortest path. Either using k gives you the shortest path, or not using k gives you the shortest path. Let's write down the shortest path when we don't use k. The shortest path when we don't use k is what? Good. dxy k minus 1. It's exactly what we had before. And presumably we can calculate this before we calculate this. So this will depend on this. This is like the situation in the combinatorial binomial coefficient where you do not include that specified object. So it becomes n choose m minus 1. So this goes down by 1. We're going to take the smaller of these 2, this one, and then another one. What's the second one? Let's think about it for a second. The second one is we definitely know now that we want to consider the possibility when going through that node k is helpful. Using it is helpful. If you know that using it is helpful, then what's the shortest path from x to y that uses that node? It can be split into two parts. The shortest way to get from x to k, and then the shortest way to get from k to y. And the intermediate nodes there are in what set? They can be all the nodes between 1 and k. But we've already used k as that middle spot, so they can only be nodes 1 to k minus 1. So here's the two parts. X to k with intermediate nodes k minus 1, followed by k to y with intermediate nodes k minus 1. One of these is going to be shorter. Whichever one is shorter is the shortest path. This one doesn't use the kth node. It's not helpful. This one checks whether the kth node is helpful. You compare these two, and that gives you your minimum path from x to y using the first k nodes. It's easier to formulate than the other one. Just a little harder to think of this definition. This definition, this part of the dynamic programming part, the part that I can often come in and kind of write it on the board as if it's like, as if that was a part that didn't take any thought. Oh, let's just start by defining this. You know, the definition always seems like you're just beginning. But in dynamic programming, the definition and the choice of it is the whole thing. Thinking of this, everything just comes out of it. So this is the part that really takes all the thought, is defining what this means. Because if you define it the other way, you get n to the fourth. And if you define it in a really horrible way, you don't get a recursive structure at all. So you want to pick this well. And that's the really, really ingenious part of dynamic programming, is picking this well. And let me stop and answer questions about this so far. Any questions about this? Teresa, you have a question? You're looking thoughtful.
Well, on the left-hand side, when you say dxyk,
Yeah.
it uses nodes 1 through k. Uses all the nodes 1 through k?
Uses any collection. Can use any of the nodes from 1 to k.
Any or none.
Right. Any or none. Right. So in other words, what's the best way you can get from x to y? And you're allowed to go through any of the nodes on this list from 1 to k.
What is the best way?
What's the best way to do it? So like if you're in a town and you see a map and you're trying to go from here to here, but you're only allowed to use, say if k is 3, you're only allowed to use nodes A, B, and C to go through.
Well, in that specific instance.
It'll just be this.
Yeah.
Right. But if it's a really huge graph, say, you know, from Boston way over to California, and there's 20,000 nodes in it, at the beginning, if I'm only allowed to use nodes 1 and 2, then there's going to be probably not a very good way for me to get from, you know, New York to Los Angeles. But as I add in more and more and more, say 500 of those nodes, then there starts to get a way to get across. And as I add in more, there might be a better way to get across. And this represents how much better I can do every time I add in one more city that I'm allowed to pass through. Okay? So if there happens to be like a little portal from New York to LA that doesn't use any intermediate nodes, you know, you press a button and it's science fiction, then actually you would never get any better by adding more k. dxy1 would be the best. So like in this example, going from A to B, there's no intermediate nodes. We're going to add in all the other intermediate nodes as possibilities as we go through this calculation, but the shortest path from A to B is going to stay 1. So dxy0 is going to be as good as dxy1 and dxy2 and dxy3 and dxy4 and dxy5 when x is A and y is B.
It just seems like an incredibly broad statement.
It does. Yeah. Yeah. It's true. It seems like it's too vague and you would stop there and you wouldn't bother. But if you just push it, you get this nice relationship. But this thing comes up a lot. It comes up in making change for coins. It comes up in the knapsack problem that we'll do in another lecture or two. It comes up a lot, the same idea of are you going to use this specified object or not? Yeah, Michael.
I don't understand what the difference between the two parts of the min is. Why are they calculating something different?
This calculates the shortest way to get from x to y if you're not allowed to use the node k. And this calculates the shortest path from x to y if you specifically are insisting on using the node k. You're insisting on going to k and then going from k over to y. So for example, if x was a, let me do a good example. Let's say x is b. I'm going to add in another edge here. If x is b and y is a, and k is 0 and k is 1. Let's try both of these. If x is b and y is a, and k is 0, then I can definitely get from b to a with no intermediate nodes in step 1. Now let's figure out the best way for me to get from b to a with one intermediate node where, here, I'm just going to make it 5. Now I can use all the intermediate nodes. So I'm allowed to use E now. So either I'm going to go directly, using less than those 5 intermediate nodes, or I'm going to go through the 5th one. And one of those is going to be shorter. So the top represents not using the 5th one, and the bottom represents using the 5th one. That didn't help.
I think
Yeah.
so.
Yeah. I should erase that graph and put a better graph up, because it's too small to see what's going on. Want to think about it for a minute? Are there other questions? Yeah.
I'm kind of confused how this is specifically dynamic programming, because when you first introduced dynamic programming, you kind of distinguished dynamic programming versus a traditional recursive method of Fibonacci, and well, this is very clearly recursion.
Right.
So what makes this specifically dynamic programming?
Nothing yet.
All right.
It's a good question, right? This is nothing but a recursive relationship. This is just math right now, so far. If we ran it recursively, we would get a horrible recurrence equation. It would be exponential and it would really be bad. But what we're going to do is we're going to build it up from the bottom up. And that's what makes it dynamic programming. Yeah, good door.
I have a problem with the notation. In the first case, k will be a number. So it's going from one node to another in a maximum of k steps.
Yeah.
In the second case...
You mean in the one we did yesterday?
No.
No, here? No, this doesn't mean the number of steps. This means
The number of nodes you can pass by.
which nodes, actually.
Oh, so you have specifically...
Yeah, and that's what lets us cut it down.
Okay.
If this number is like 4, it means you're allowed to use nodes 1, 2, 3, 4 in between going from x to y. But no other nodes can appear on the path from x to y except the ones 1, 2, 3, 4.
Okay.
That's what it means. So it has nothing to do with how long the path is.
Okay.
The path can be very short or very long. It's different than the other way, where we're building it up by the size of the
That
path.
would mean in this case we could use A, B, C, D.
Exactly. If that k was 4, you could use A, B, C, D in the middle. So of course, when k gets to be n, then that's the complete shortest path, because you can use any intermediate node and there's no restriction. Yeah. Other questions? Okay. All right. So how should we compute this? Doug said, it's just recursion so far. It's not dynamic programming yet. But if you compute this recursively, you get lots of multiple calls. These things start to overlap like crazy. You can imagine. So we're going to do it from the bottom up. Why? Because there aren't so many of these subproblems total. X ranges from 1 to n, y ranges from 1 to n, and k ranges from 0 to n. So the total number is only n cubed. And that's the classic dynamic programming scenario. You make a recursive structure. The total number of your subproblems is polynomial. Don't bother using your recursive structure to generate the subproblems. Just generate them yourself from the bottom up and make sure you hit everyone exactly once. And don't do anyone more than once. The worst that could happen is you get n cubed. Okay? So that's our goal. But which do we do first? What does the loop look like? This little thing right here is going to sit in the middle of a loop. Right? It's going to be a minimum calculation of 2 other values which are sitting in an array. Right? So you're going to look these up. In order to look these up, you better do these before these. So we have to put a big loop around this. Before we enter the loop, we have to initialize dxy equals wxy. This means that dxy is initialized to the actual weights of the graph. This is dxy 0. Okay, and this is for x and y equal 1 to n. That's the initialization. Okay, that's copying the actual two-dimensional graph data structure into the D array, which we are now going to update and update and update over and over again, just like we did last time. And now we have k starting at 1 and going all the way to n. We're going to do dxy1 and then dxy2 and dxy3 and dxy4 all the way up to dxyn. And we're going to do it k first because we got to do dxy1 before we do dxy2. And we got to do dxy2 before we do dxy3. We got to do them in that order because k depends on k minus 1. All right.
Would you want to n?
I think so. I mean, n minus 1 we could do? Or
Minus 2?
no, because, well,
What's the k in the middle?
this is not the number of nodes that you're allowed to use in the middle. It's actually a particular sequence of nodes. So if x and y, happen to be a and b, and the last one is g, then you want to be able to include g, and the only way to do that is to let this go all the way up to n. So you really do have to go all the way up to n. You can't cut it down to n minus 1 or n minus 2. And that's a good question. That's a good thing to think about. All right, so inside this loop, we're going to have this exact same thing, and it looks like this. For I, j equal 1 to n, dxy is the min of whatever it was before, and the sum of these two. That's the whole algorithm. You start going from 1, you go all the way up to n, and inside your loop you go through every pair of ij and you make this calculation. You check the new value, Jesus, xy, sorry. The new value of shortest path from x to y is going to depend on the old values of k minus 1. One choice is that you don't use the kth value. That's this one. That it's just the best you had was the one before. And the other choice is that you do use the kth value. That means you look up this one, dxk and dky, and you add them. One of them is going to be shorter. Whichever one's shorter goes back into the array, and now this represents the kth value. These represent the k minus 1th values. These represent the kth values. Okay, it looks like the same array, but these are the old values, these are the new values. And then it goes back. So it's a triple loop, and it's n cubed. And there's just a minimum calculation inside with a lookup in a two-dimensional array. So the whole thing takes order n cubed. Doug, yeah.
I'm curious, does it matter the order of the loops, whether the k equals 1 to n is on the inside or on the outside of the for x, y, 1 to n?
So I'm going to let Doug write the next problem set. That's like the most famous problem that you get in this thing. It's like, I must have seen it in a dozen textbooks and 25 different exams that ever have a question on this problem. They go, what if you put the k on the inside instead of the outside of the xy? Does it still work? And if it does, explain why, and if it doesn't, explain why not. Excellent question. So now you have to answer it, doing some pedagogical trick to see if somebody could think about it and say, whoa, that doesn't work. I mean, this really works. This is okay. The question is whether the other way works, whether you can have the xy on the outside and have the k on the inside. Let's think about what that would mean. We have the xy on the outside going from 1 to n, and on the inside we'll have k going from 1 to n. That means, let's fix it. Let's say we got up to a particular xy, like x being 6 and y being 9. Okay, so now we got d6, 9. And now we're going through this loop on the inside. So d6, 9 is going to depend on what? It's going to be d6, 1 plus d1 plus d1, 9, or What's the other one it could be? Or whatever it was before. Right? Those are the two choices. Right? And then you're going to check D62, D29. Right? Is it okay to do it this way or not? What do you think? Is it okay to put the K loop in the inside or not?
You eventually say you get to node 12, we don't know anything about node 12 or distances between anything, node 12 and anything else, because we haven't gotten there on our XY yet.
All right, so let's write it down like this. 6, 9, it's a good idea. Let's say we're trying to do 6, 9, 1. What does 6, 9, 1 depend on? Depends on, I'm going to put the K's in because you'll see what goes wrong now. It depends on 6, 1, 0, right? And 1, 9, 0. Right? That's what these two depend on. D691, the pair 6, 9, these two depend on D610 and D190. They also depend on the old value of D690. Now we've already done D690. That's okay. This one is done because we did it at the beginning. And this one's never going to be a problem. We will always have computed this one because the K starts at a lower number and gets to a higher number. And these two xy's match these two xy's. So I'm going to check this one because this one's never a problem. But what about here? 610. We have that, and we have 190 because that was the initialization case. Now let's bump it up to 2. Do we have 611? Did we do that yet?
Yes.
We did because 61 happens to come before 69. Did we do 191? We did it because 19 happens to come before 69. So we think, okay, I got those two. But can you come up with an example where I wouldn't have the ones I wanted? That's what Chris was saying a second ago. What if, say again?
6, 9, 12.
6. So this should be,
No, well, that's 9, but we're looking at K equals 12 now.
so this is 6 to 12, and this is 12 to 9. Right? We're going to get to there. We're going to get to K equals 12 sooner or later. 6, 9, 2 depends on 6, 12, 1 and 12, 9, 1. But we haven't done 6, 12, 1 yet. We haven't done 12, 9, 1 yet. We won't get to them until we finish 6, 9 and go back to the IJ loop. You can't just sit here at 6, 9 and finish it up because it's going to end up depending on things that haven't been computed yet. The only values we have for 6, 12, and 12, 9 are the ones we did last time through when K was equal to 0 at the very beginning. So if you take it out of order, you can find counterexamples where your loop is dependent on things that you haven't computed yet. It will actually run because the actual values of these are simply the old 0 values, but it will give you wrong answers. Does that make sense? That's a very subtle and interesting point, and it will really help you to understand the algorithm if you try to answer it and go through it yourself again. But the answer is you cannot take the K loop and stick it on the inside because some of the cases that will show up will depend on values that you need to have computed before, but you haven't computed them yet. You need to be careful to compute your values in the right order. Okay. More questions? Any questions? Yeah?
That's kind of a broader question. If we're talking about recursion versus dynamic programming,
Yeah.
and if you are able to memoize your recursion, is there any call for dynamic programming?
They're the same idea. Memoizing recursion and dynamic programming is the same idea. The differences you see is that in dynamic programming you need to come up with the right order of doing things, and in recursion you just store it and look it up. So
It seems to be dynamic programming, since you compute things you might not actually use, that I'm not able to think of a reason for doing it.
If you had to solve a lot of different problems using the same piece of data.
that's one idea.
Good idea.
If you were going to, but, well, What's the idea of memoizing? The idea is that when you get a call to a subproblem, before you actually go ahead and run it, you check to see if you've called it before. Right? So there's a little overhead there. You have to check and look up to see if you've called it before. And it's never going to get exponentially crazy, because if you don't call it, then you don't call all its children either. But you still might actually check every single subproblem twice just to look it up before you actually do it. So maybe that trade-off is enough, because just 2 times the lookups might actually add up to all the subproblems that you're doing, since each one only takes 1 step. It's not hard to do these subproblems. So it's a trade-off. And sometimes memoizing engineering-wise would be better, and sometimes it wouldn't. But it usually doesn't affect the overall time complexity. Yeah. But it's a good point. But I think it's more of an engineering issue than anything. Yeah.
And just make sure that I understood. The third number in each of these should be 12, 11, 11, and 11. For the D69, that should be 12, right? With the example that you just did, rather than 2.
D6, 9, 12 should be 6, 12, 11.
Right.
And that should be 6, 12, 11, 6, 9, 11.
6, 9, 12, 6, 12, 11, 12, 9, 11. Yes. You're, right. And this would be 6, 9, 11. Right. Right. Yes. I was careless. You're 100% right. The key idea, though, is that these numbers here are further down in the IJ list than this number, so that the values for these numbers here are really the 10 values and not the 11 values that we want. So what you end up doing is, for the values here that are bigger than this IJ value, you end up having 6, 9, 12 dependent on 6, 12, 10 and 12, 9, 10, and that's not right. Right, but good clarification. Good point. Other questions? All right. Let's switch gears then. Get away from shortest path and graphs and move on to a mathematical algorithm. All right, I got to go remind you back stuff we did a couple months ago, maybe in September, when we learned how to multiply matrices together. When you multiply matrices together, the number of columns in the left matrix needs to equal the number of rows in the right matrix. Because when you multiply them together, your answer is going to end up being 10 by 30. And this value here is going to depend on this row and this column. You multiply each thing successively and you add them. So the number of columns needs to equal the number of rows. And doing the dot product of these 2 vectors gives you that entry. If you want to get the next entry down here, you do the dot product of the second row with the first column, and that gives you the next one. And if you calculate the time complexity of matrix multiplication without doing anything fancy, it's just this times that. It's just each of the entries 10 by 30, and each one takes 20 steps to do. So it's 10 times 20 times 30. If they were all equal, it would be n cubed, if they were square matrices. I mentioned that you can do better than that. You can do n to the 2 point something, but forget that for now. Let's just do n cubed and work with that. And we're not talking about multiplying matrices and analyzing the particular multiplication of 2 matrices today. We're going to talk about multiplying lots of matrices together and what's the best order to do it. And you've seen this problem before, but now we're going to do it from an algorithmic point of view. All right, so let me stop so far. Questions? Everybody remember what I mean by multiplying matrices? All right, so let me show you what the issue is. Let's say you have a whole bunch of matrices you want to multiply through, the whole chain of them. And here are their dimensions. Say this one's 10 by 20, this one's 20 by 10, This one's 10 by 15. This one's 15 by 20. This one's 20 by 10. Now you can definitely multiply these together because every successive number of columns matches the number of rows in the next one. 20, 20, 10, 10, 15, 15, 20, 20, 10. The thing is, there's a lot of different ways to do this. You can associate matrices any way you want as long as you don't flip their direction. So we can do, here's an example. We can do these three first, and in these three we can do, say, these two. And then here we'll do these two, and then we'll do all of them. Did I get it all? Looks okay. So we'll multiply these two together, and then we'll multiply this one times this one. We'll multiply this one times this one, and then we'll multiply this result times this result. Now that's going to give us some number of multiplications altogether, but there's a lot of other ways we could have done this. The number of ways there are of multiplying these matrices together is equivalent to the number of ways there are of putting parentheses around them. Okay, there's a lot of ways to put parentheses around things. It's the same as the number of trees that have more or less this many nodes. There's a lot of trees, there's a lot of parentheses expressions, and they're more or less equivalent to 4 to the n. 4 to the n divided by square root of n. It's a very, very big exponential number. So here's not the way to do it. We are not going to try every possible way to parenthesize these things, calculate what we get, and take the minimum, because that'll be an exponential time algorithm. We're going to do it just once for this example to make sure everybody knows how to calculate the total, and then we're going to discuss how we're going to get the minimum. So let's just do it for this example, calculate how long this one takes. How long does it take to multiply these two? How many steps? 10 times 20 times 10. So this is, I'll write it up here, this is 2,000, and we get an array of size, what's the size? 10 by 10. Okay, let's move over here. How much does it take to multiply these two? 3,000, right? 3,000, and we get an array of size 10 by 20. Then we have to do what's next? This one times this one, according to our parentheses. That's going to be another 2? Yeah. Good. What's the array that we get from here? Size 10 by 10. 10 by 10 by 10 is going to be another 1,000. Now we're done. We got a 10 by 10 array. We're always going to get a 10 by 10 array when we're done. It's just we might take a long different path to get there. And this makes 5, 7, 8,000 operations altogether. Total. Okay. This seems pretty good, actually, right? Because the last one's only 1,000. It's actually not a bad choice. You can imagine as you make the parentheses join up in different ways, you get a different sequence. Okay, so what's your gut instinct? Think this is the best or not the best or something very bad, very good? We just picked it at random. The chance of it being the best, unless I specifically chose it to be the best, is pretty slim. And it's not the best. The best we can do is actually 7,500 in this collection. But how do we figure out what that is? Just choosing all the different parenthesized ways is terrible. So we need a better method. Okay? Now let's talk about that method. All right, so this is the moment of truth. Once I write down the definition of what we're going to try to compute, of what the subproblems are, everything else is going to flow from that, and it's going to be more or less mechanical and just figuring out what things mean. But this is the step that requires some ingenuity. We need a problem that we're going to compute that has a total number of subproblems that are polynomial, that are relatively small. So how are we going to do that? Yeah.
Can you do this as a graph problem?
How would you do it as a graph problem?
Each matrix is a graph and connect the ones you can multiply together and then you worry about
Oh, well, well, the only ones you're really allowed to multiply together are the ones that are left to the right of each other. I mean, you're not allowed to move them around. So I mean, the graph would just look like a straight line. And yeah, the real issue is how we parenthesize it. You might be able to convert the parentheses structure to a tree, but then you've just changed the issue of how do you go through all these different trees without actually enumerating each one. And that's the same kind of question, it's just in disguise. We want to be able to build up all the different possible trees out of a polynomial collection of subtrees instead of getting the exponential number. So you can think of it that way, but we still need to have the recursive relationship. So here's what we're going to try. Let's call capital M for matrix multiplication to be the best way to multiply all the matrices from matrix I up through matrix J. Sometimes, if you just do the obvious thing, you can come up with a recursive structure. All this means is if I have the matrices on the board and I number them 1 through 5, I write down M15. That's what I want to figure out. The best way to multiply the matrices number 1 through number 5. Right, and hopefully that will depend on the best way to multiply the matrices number 2 through 4, and number 3 through 5, and numbered 1 through 3. Okay, those are the subproblems. Multiplying substrings in some sense of those matrices. All right, so Mij is the smallest number of multiplications to multiply array I through J inclusive. So in our example, we want M15. That's what we would like to get. And hopefully we can come up with a recursive structure where M15 is dependent on the shortest paths of the smaller examples, M14, M13, etc. And then notice that that recursive structure gives you an exponential repetition of subproblems. And then go ahead from the bottom up and generate these subproblems in a dynamic programming approach. How many subproblems are there total? What's the worst it could be? You don't have to get it exact. Just give me the worst if it's polynomial. What's the worst it could be? This number can be anything from 1 to the number of matrices, and this number could be anything from 1 to the number of matrices. Well, it's never actually going to be that bad, because if you start here with 2, you can only have 3, 4, 5. You can't have 2, 1. That goes backwards. But the worst it's going to be is n squared. It's actually going to be the number of triangle numbers, because 1 can go with 2, 3, 4, 5. 2 can go with 3, 4, 5. 3 can go with 4, 5. So it's really just 1 plus 2 plus 3 plus 4. The number of subproblems is a triangle number. It's about n squared over 2. So if we just figure out all these subproblems, we'll be okay, no matter how the recursive structure works. But we're still at the hard part. We still haven't come up with a recursive structure. We're going to do that in just a second. Okay. Let me write down our example that we did before again. 10 by 20, 20 by 10, 10 by 15, 15 by 20, 20 by 10.
I mean, if 7,500 is the best and we randomly picked 8,000, I mean, sort of how bad can it, is 9,000 the worst, or would that go to 50,000?
It depends on the numbers, but I didn't calculate the worst, although you could do it.
I guess intuitively it seems like this may be a lot of work, and if the number of operations we're talking about is a small range around an average.
Right. Well, I think you can come up with examples where it wouldn't be a small range around an average, but your idea is really important because there's this idea of an approximation algorithm. If you can do something fast and not bother to go through a lot of effort, and you're off by at most 10%, then let's do it. But normally you don't use that for an algorithm like this, which is going to be polynomial. You use that for an algorithm that's typically NP-complete. If you have a problem that's NP-complete and your algorithm is exponential, but you can come up with a fast one that, say, gets within 90% of the right answer, then go for it. And we do that with things like traveling salesmen and various other problems. So it is a method that we use, but I never read anybody using it in this problem, because I'm not sure you can really bound how far away it is. Okay. I think the best way to see this recursive relationship is to start the example first before I write down the recursive relationship, and then it'll make some sense. So here's what we're going to do. We're going to make a little chart for ourselves. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. These represent the arrays numbered 1 through 5. 1, 2, 3, 4, 5. And we would like to figure out this one. That's the box we want, M15. Some of these boxes don't exist at all. I should kind of show you which ones don't exist, or you show me. All these over here don't exist. There's no 2, 1, and there's no 3, 1, and 3, 2. Those aren't there. Those don't correspond to anything. You have to go from left to right. All right, so let's do, what are the base cases? What are the easy ones? What are the ones you can do right away?
1, 2, 2, 3.
Well, there's easier ones than that. Well, 1, 1, right? What about 1, 1? What does 1, 1 mean? The smallest number of multiplications to multiply array 1 through array 1 inclusive. How long does it take you to multiply a single array by nothing?
0.
Doesn't take you any time, right? Just sit there. Well, those are easy cases. 2, 2, 3, 3, 4, 4, and 5, 5. That means you're not doing any multiplying. It costs you 0. You got to like your progress so far because, I mean, if every subproblem is so easy to do, you know, the mountain's only over here. We're almost there. So it's looking good. Now, how much does it cost to do 1, 2? There's no choice in multiplying arrays 1 through 2. You can only do it one way. So the whole next diagonal is going to be just how much it costs us to multiply those 2 arrays. So let's write those numbers in. 1, 2 gives you 10 times 20 times 10. Right? 2,000. This gives you, that's 2, 3. 3,000. 3, 4 gives you, I want you guys to do it, right? 3,000. 4, 5 gives you 3,000. There was no choice there. Right? There was no idea that we had to do anything. We just, boom, it was easy. But now for the first time we have a choice, 1, 3. And this is what's going to motivate the recursive relationship. We want to figure out the best way of multiplying these 3 arrays. Well, we could also do all 1 through 5, but that seems too hard. Let's work our way up. 1 through 3. What's the choice here? Either we do 1, 2 first, and then multiply by 3, or we do 2, 3, and then 1 times that. Okay? 2 choices. Where are those choices? How can I find them? I know what it costs to do 1, 2. I can just look that up. So we're right here, right in this spot. What does it depend on? The cost of doing 1, 2. If I do 1, 2, how much more does it cost me to get the third one in? If I first do 1, 2, and then I do 3, I could look up the 1, 2 over here. But to do the last multiplication, I have to do a calculation. What's the size of the 1, 2? It's 10 by 10. So when I multiply by the third one, I get 10 by 10 by 15. I get an extra 1,500 in order to do it that way. Let's keep track, plus the 2,000 for my startup. So I'm going to write that down. M13 is, if I do the 1, 2 first, I get 2,000 plus 1,500 for the gluing it together. Where did the 1,500 come from? This is, I'm going to write, this is the 1, 2 case. And the 1,500 came from dimension rows of number 1, columns of number 2, columns of number 3. That's where that 1,500 came from. 10 times 15. Right? Okay, what about, is that it? Is that my answer then? I write 3,500 in there? No, because I got to check the other possibility. And the other possibility is that I do M23 first. Where's that? It's over here. These two help you get this. So here's the choice. 2, 3. You get 3,000 plus the amount it's going to cost us to multiply 1 by the 2, 3 combination. That's going to be 10 by 20 by 15, which is another 3,000. And you look and you ask yourself which one is smaller. The top one's smaller. Therefore, we write 3,500 in this box. And we finish that one. Let me stop so far. Questions? Everybody get it? There's something important when we're all done here that we're going to need to do. When we're all done, we're going to have a number here that'll say 7,500. Will that tell us the actual way to multiply them together? No, it'll just tell us what the smallest number of operations it takes. But what if we wanted to backtrack after that and figure out what the actual best order was? Then we better do something along the way here to leave breadcrumbs so we can find our way out of the cave. And if we don't do it, we're going to be sad because we won't be able to figure out what we want to figure out. So be careful. How do we remember what happened here? Basically, we just calculated M13, and we just figured out what should happen with M13. Namely, we should do 1, 2 first, and then we should do 3. All right? I'm going to remember that in the following way. I'm going to put the number 2 there. That means I go all the way through 2, and then I do the rest. 1, 2, and then I multiply by 3. If this had been the faster one, then what number would I have written in? I would have written in 1. I go all the way through 1, and then I do the rest. Okay, I write in the point at which I split the multiplication up into 2 parts. You'll see how this works in the next example. By the way, there are these numbers here too when you're just multiplying 2 arrays. If I'm multiplying 1 and 2, then it's kind of trivial here, but then I do 1, and then I do 2. If I'm multiplying 2 and 3, I do 2, and then I do 3. So these numbers are just going to be 1, 2, 3, 4. They always are. That first diagonal is always just 1, 2, 3, 4. Let's go now to 2, 4. What order are we filling this table in? It's not, left to right, bottom down. It's in a particular order. Right, diagonals, moving our way up to the tippy top. The book has a nice feature where they draw it this way. Like a triangle, and the diagonals are at the bottom, so you just work your way upwards. And I would do that, but I goof up when I draw it like that. So I draw it like a grid and remind you that you go diagonal by diagonal. And what's increasing here is the difference between the size of the arrays. Here the difference is 1 through 5. It's 4. Here the difference is 0. Here the differences are 1. Here the differences are 2. Here the differences are 3. 1 to 4, the difference is 3. 2 to 5, the difference is 3. How many arrays you're considering? So we're working from the smallest number of arrays to the largest number of arrays. That's the difference between the I and the j. And whenever you're moving upwards relative to the difference in these two, it corresponds to moving diagonally. This happens a lot in dynamic programming. You don't always go left to right, up, down. Sometimes you do, but sometimes you move this way diagonally. All right, let's do a calculation for 2, 4. Easy? All right, who wants to help me do 2, 4? Dimitri, you've been sick for 2 days, right? You feel all right? All right. Too easy for you, right? All right, that's what I thought. That's what I thought. All right. So, Chris, you get to help me. Dimitri begged off.
I can't read the board.
That's okay, Dimitri can. I got to split 2, 4. I'm figuring out the best way for me to multiply matrices 2, 3, and 4. So where are the places I can split this up? 2, 3, or 3, 4. So if I do 2, 3,
Those are the only options, right?
because there's only 3 of them, right? So if I do 2, 3, I can look that up here. 2, 3 is 3,000. And then I got to add in the amount it takes me to multiply in the fourth one. So the 2, 3 array is going to be 20 by 15. And multiplying in this, I get 20 times 15 times 20. It's big, right? 6K? Check my own notes. Yeah. And then what if I do the other possibility, 3, 4? I look that up in my chart. That's also 3,000. And what do I have to pay? 20 by 10 by 20. 4,000? So the smallest is the bottom one, is the 3, 4. So I write 7,000. And what do I put here? We're going to split after the 3. Well, we're going to go through 3 and then we're going to go past. So I put a 3 here. I really store these numbers. These numbers are going to be used later to reconstruct this ordering. So we need to store them. All right, good. Let's just say what this one is. I think everybody gets it. This one turns out to be 4,500 and a 3. But I do want to do the last 3 because there something less trivial happens. In this example, when you're looking at the possibilities, it's either you do the first 2 and then do the last one, or you do the first one and then the last 2. But when they start to get longer, how many different things do you have to consider? And then in general, how many different things do you have to consider? And then we'll write our general recursive relationship, now that we've done it enough times with enough examples. So let's do this by moving our way up to the next diagonal, M14. How many different ways can you multiply M1 through 4? Well, you don't want to consider all the different ways to parenthesize it. That's what we didn't want to do at the beginning. But we can decide at what point to split it. Either we can do 1 and then do the rest of these, or we can do the first 2 and then do the last 2, or we can do the first 3 and then do the last 1. Now, each one of those is a tough problem in and of itself, but we've done them all already. For example, let's say I tried this one first. How much does it cost to multiply 2 through 4? We've done that already. Just look it up. It's 7,000. So this is where we split after 1. It costs 7,000 to do 2 through 4, plus how much does it cost me to do the final multiplication? 10 by 20 by 20. 2 through 4 has been done. So 2 through 4 gives you a 20 by 20. To multiply the last 2 together, I get 10 by 20 by 20. That's 4,000, right? So that's 11. That's a lot. The next possibility is I split after 2. How do I look that up? I got M12 and M34, and I look those up in my chart. Here's 1, 2. Here's 3, 4. They add up to, I'll write them out, 2,000, 3,000, and multiplying together costs 10 by 10 by 20, which is 2,000. The last one is that I split it after 3. That's M13, which is here, 3,500. And what does it cost me? It costs me 10 by 15 by 20. So that's another 10 by 15 by 20. 3,000, right? So which one is the smallest? It looks like the bottom one, 6,500. And I write in number 3. The number I write in corresponds to the point after which I do the splitting. So as the things get longer, the choice is not how you parenthesize it, but simply how you split it into 2 subproblems. Here's the big picture. If I want to multiply a whole bunch of things together, or I want to parenthesize a whole bunch of things together, my real choice is, first I'll parenthesize this part, then I'll parenthesize the other part. Each of these is a recursive call. I can look them up. I've got n different ways to do this. I can make the break at any one of n minus 1 places. What does the recurrence equation for this look like? T of n, there's n different places to do the break. Every time I do the break, I get things of different sizes. The worst case would be something like T of n equals n times T of n minus 1, some horrible looking thing. So if you do it recursively, it's bad. It's never quite that bad because when you split it evenly, you don't get Tn minus 1, you get smaller things. But if you do it recursively, you get multiple computations and you get a lot of complexity. The thing is that we only have a polynomial number of these subproblems, so we build them up from the bottom, just like we're doing now.
Is that the recurrence equation for Catalan numbers that we computed at the end of discrete math?
Yes, yes, right. And Catalan numbers are the same as this, because that's the number of ways to parenthesize things. Exactly the same, right. All right, so let's write a recursive relationship. How does Mij depend on the other m's? Well, basically, you can do the multiplication from I to any place in the middle, and then do the best multiplication from that next spot to the end. It's Mik plus, what's the next spot to the end? I through k, so k plus 1, the next one, through j. Look up this, see what they add up together. In the really simple examples, one of them sometimes ends up being 0. You know, I ends up equaling k, so we got 0 in some of the earlier examples. 0 plus 2,000, and then some other issues. But this isn't it completely. Here are the two subpieces. What's the last piece? It's the gluing of the two together, the last multiplication. So now we need some notation, and it gets a little ugly. But what the book typically does, and it's a nice notation, so I kind of like it. I didn't use it in my notes, but the book uses it. They give these dimensions names. If this is array 1, then this dimension is called P0, and this is called P1, and this is called P2, and this is called P3, and this is P4, and this is P5. Okay? The intermediate ones match. So the column for 1 is the same as the row for 2, and they're both called P1. So P0 through P5. You have 6 different dimensions with 5 arrays. Right? Because the middle ones match, and you have 2 extra at the ends. So if we label the dimensions this way, then what do I glue on there? Let's do an example first. Let's say I'm doing 1 through 4. And I decide to split it at 2. Then what does my gluing cost? It costs 10 by 10 by 20. It costs P0 times P2 times P4. If I'm splitting it after k, what's it going to cost? I'm splitting it after k. What dimensions am I going to use?
P0 plus PK plus PN.
Not P0, because we're not starting at 0 here. We're starting at I. So if you're starting at I, say you're starting at 2, what would this one be called? What's this dimension? Good, Pi minus 1. Right? If you're at P2, then the row here is P1. If you're at P3, the row here is P2. So it's Pi minus 1. Oh, you're ahead of me. Pk, let's make sure that's right. Pk, because it's the same. And then Pj, because it's the same. Good, exactly. That's a nice notation. In my notes, I made it a little more semantic, but not as easy to code. In my notes, I wrote the row of array I times the column of array k times the column of array j, because I thought it made sense. But it's nice to remember that these dimensions can be stored in an array called P and referenced easily. This is it, except we have to do this for every single k. So we want the minimum of this over every k. And what does k range from? K can be equal to I. Right? You can just have 1 on its own and then the rest. So k can start at I, and k can go all the way up, including j. That's the recursive relationship. And that's the recursive relationship that we are doing bottom up in this example. We'll analyze it in a second, but let's finish up the actual example. I'll write in the values. If you finish this one, you get 6,503. And if you finish this one, you get 7,502. Okay, let me stop for a second. Here's what it looks like. To code this, it's a little bit ugly because you have to set the loops up so that you have a loop called diagonal. As diagonal goes from 1 to 5. And then you have to generate the ij's relative to that diagonal. So it's a little bit ugly. If you have trouble with indices and loops, this is the best thing to practice because you got to take a diagonal and have it generate these things in order. So you want to generate all the things that are 0 apart, all the things that are 1 apart. So you're going to have a loop that starts here. It'll go 1, 2, and then 2, 3, and then 3, 4, and then 4, 5, and then the ones that are 2 apart. So this will go up by 2, and then the things are 2 apart. 1, 3, 2, 4, 3, 5, finally 1, 4, 2, 5, finally 1, 5. The book has the code written in detail, and you can look at the indices and work them out. But basically, it's just the way of generating the ij in this order. All right, 2 things left, and then we'll quit today. Number 1, how long does this take? And number 2, how do we use these numbers that we stored to print out a parenthesized expression of this matrix multiplication? Those 2 things. All right, so first things first, how long does it take? We got to look at every one of these once. Just once. And how much work do we do for each one? How much work do we do for the ones in the bottom diagonal? Very little. Nothing. How much work do we do for this one? How many choices are there? The 2 arrays that differ by 1, you're taking the minimum of exactly one thing. So I'm going to write this takes 0 steps. This diagonal takes 1 step for each one. This diagonal takes 2 steps. This diagonal takes 3, and this diagonal takes 4. That's the number of different sub-things that I look at. Now, this is also worthwhile to see geometrically. Let's look at this one. Which boxes does this one depend on? It depends on pairs of boxes. M15 depends on M11 and M25. Where's M11? It's here. Where's M25? Here. I'm going to check these off. The next one is M12 and M35, which is here. We're going left to right in this row and top to bottom in the column. And we're matching them in pairs. These 2, these 2, these 2, these 2. That same geometry holds at the very beginning, but you don't notice it because it's too small to notice. But this geometry is important, and that's how your actual algorithm is going to check these pairs. This pair, this pair, this pair, that pair. All right. So there's 4 different pairs. It's the distance from here to here and the distance from here to here. So what's the overall time complexity? You get this funny summation. You get 1 times 4 plus 2 times 3 plus 3 times 2 plus 4 times 1. Where 4 is really n minus 1. Right? 4 is 1 less than the number we started with. Did we ever do a summation like that? I don't think we did. A whole month of discrete math, we never did this one? The numbers are running from 1 to n in one direction. The numbers are running from 1 to n in the opposite direction. Well, it's too bad we didn't, because if we had, we could just say what the answer was, right? But I mean, it came up right here. Here it is. It's very natural. The one that has the fewest elements takes n minus 1 steps. The n minus 1 cases that at the bottom take 0 steps. The n cases take 0 steps. The n minus 1 cases take 1 step. So you have this inverted multiplication. What do you think this turns up to be? Well, let's get a worst case on it. Let's go to worst case. How many possible boxes do I have altogether? It's 1 plus 2 plus 3 plus 4, right? It's 1 plus 2 plus 3 all the way up to n minus 1. So that's a triangle number, and that's about n squared. Okay? That's just this part. That's pretending that all these numbers here would be 1s. What's the worst any of these numbers can be? They can be n at the worst. So the worst thing we'll ever get is n cubed. Maybe this is better than n cubed if you actually add it up, because after all, we got the higher numbers with the lower ones and the lower numbers with the higher ones. Remember when we did that with a heap? Instead of it being n log n, it turned to n. Except there, one of the numbers was going exponentially and the other one was going linearly. And here, they're just both linear. So I'll give you the answer. The answer is that this doesn't end up better than n cubed. It's a constant factor better than n cubed, but this summation is big theta of n cubed. All right, so if you're going to add up all the numbers from 1 to n and multiply them by the numbers in reverse order and do them in pairs, the sum ends up being order n cubed. And this algorithm, therefore, is order n cubed. The proof of it is a relatively detailed discrete math argument, which has to do with the sums of the consecutive squares of numbers. 1 squared plus 2 squared plus 3 squared, that's order n cubed. If that's order n cubed, this turns out to also be order n cubed. And we can talk about it some other time. Nobody wants to hear any more details. All right.
So to get the actual path, you just look at that 2 and that splits it?
Yes. Let's do that. That's the last thing. Neil's saying, can we finish now? We're going to be done in 5 minutes. No more thoughts. Just let's do it. All right. Let's use these numbers to print out a pretty picture of the multiplication. As I said before, whenever you store these numbers along the way in your dynamic programming, extracting the actual solution that gives you that minimum is almost always a recursive solution. A recursive solution that goes back in your table and looks at those numbers you stored. So, if you want to figure out the best way of multiplying matrices 1 through 5, then look at that number 2. That number 2 says we split it after the second array. So it looks like this. Okay, and what goes here? We'll call this matrix number 2. This is matrix number 1. And this is matrix number 3, 4, and 5. That's all we know so far. We know that in the last step, we split it over there. We're going to work our way back now recursively to figure out where we split it in each of the subproblems. How do we do that? Where do we go? If we know we split it at 2, then we need to go to the box that does 1, 2, to 2, and we need to go to the other box that goes 3 to 5. And they're in here. So this 2 tells us to go back to here, and then go back to here. And we're going to do the left one first. So we go back to 1, 2. This says you split after 1. That means it looks like this. No choice, right. And what happens when you split that up? That means first you do M1, then you do M2, and that brings you back to these 0 things which don't have anything in them, and you're done. You could also just stop when you get to this diagonal, when you get to 2 that are 1 apart. All right, now let's do the other side, M3, 5. There we split after 3. If we split after 3, then we go ahead and put parentheses here and here. And we split into a single 3, 3, which is just this, and then 4, 5, which we look up. And 4, 5 is just after 4. So we put that multiplication in. And this is the multiplication that gives you the best. So in the notes, I wrote a little recursive routine that actually will print out exactly this. The open parens and the closed parens and the stars in the right order. by doing the recursion just like this. So it puts the open paren, and then it hits this M1, and then the star, and then the M2, and then the closed paren, and then it works its way through in the recursion. It's kind of a post-order traversal of this parentheses tree. And you can look at that code. But the idea is really basic. Start from here and recursively work your way back. How long does it take to recursively work your way back? What's the worst case? Why is it n? That's right. Why is it n?
Because we could conceivably have an array where the best thing is to go M1 times this and M2, so that you have to go back through the
Well, you're right, but even in good cases, it takes n.
You have to put something between
Yeah.
M3.
Every single time you look at one of these things, that's one step, and it always brings you back to other cases, and every one of those other cases, you split it in one step, and every time you split it, you're one closer to not having to make any more calls. How long does it take you to put splits in until you don't have to make any more calls? It takes you n minus 1 step. So it always takes order n. It's linear time. And it's also typical that the recursive backtracking through any dynamic programming tends to be faster than what you did on the way up. Because you're not looking through everything once anymore. You're just zigzagging very carefully through the ones that you need to. And that happens in every single dynamic programming problem, each one in a mildly different way. All right. Let's quit.